All right, so we're on chapter 4, section 3, and we're talking about some different families of organic compounds. And we're going to talk about functional groups specifically. So everything we've talked about so far, we were really only talking about groups that have carbon and hydrogen, and that's it. But there are other atoms present, and we call those heteroatoms. And so a group of atoms that are bonded together in a particular way is a functional group. So you'll always see the same structure in a functional group. It'll always be the same elements in a functional group. And so these functional groups give the molecules, the organic compounds, particular characteristics. And so we can classify our different organic compounds into families based on what kind of functional groups they have. And because they have these functional groups, therefore they have specific properties and they have specific chemical reactions that they undergo. And so we can say, if we understand the families, we can say, okay, I know that this molecule is in this family just looking at the structure. And so I know it's going to behave in this way. And it gives us a really great understanding of organic molecules. So we've already talked about one of the functional group. We've talked about alkanes. Remember, alkane starts with an A. So it's the first one. So it's all carbons and hydrogens, right? There are alkenes, alkynes, and aromatics. Those are also carbons and hydrogens. And that's it. And we'll talk about some of those later in the other chapters, in the other sections. But all of the ones that start ALK are just carbon and hydrogen. But other functional groups contain other atoms like oxygen, nitrogen, and sulfur. And there are a lot of functional groups that contain specifically a carbon double bonded to an oxygen. And so this is an example of that, a carbon double bonded to an oxygen. And so we call that a carbonyl. It is not pronounced the way it is spelled. Of course, that would be too easy, right? But we call it a carbonyl group. And so you're going to see the carbonyl group pretty often. So when we talk about different molecules, right, we said that if you have a certain functional group, then you have certain properties. And so it's the functional group that's the reactive part of our organic compounds, our organic molecules. If you didn't have the functional group, they wouldn't undergo certain reactions. And so a lot of times when we draw functional groups, we say, okay, here's the rest of the molecule, and here's our functional group. And so we use the letter R to represent the rest of the molecules so that we can focus on what's actually participating in a reaction. And so I'll give you an example here, right? This is a carboxylic acid functional group, right? And in a carboxylic acid functional group, we have a carbonyl. So here's our carbonyl, our carbon double bonded to an oxygen. And it also has an alcohol group. So that's the OH, right? So this is a functional group that actually has two families in it. It has a carbonyl and it has an alcohol. But here's the rest of the molecule. We're not telling you how big it is or how small it is. It could be really huge. It could be really tiny. And it doesn't matter because this is the part of the molecule that's going to undergo chemical reactions and things like that. So that's what we really, really care about. So I want to show you how different those rest of the molecules could be, right? So this was our example of our carboxylic acid with our functional group. We had our carbonyl right here. We had our alcohol right here. Well, the rest of the molecule could be vastly different. If you had, for example, acetic acid, you would have a CH3. So it would be this one carbon here is attached to a carbon here, and then it has 1, 2, 3 hydrogens surrounding it. So that's pretty small. You could have palmolic acid. Now this one has lots of carbons. Remember we said every time you have a point, right, that's a carbon. So this ends up being a really huge molecule. But these two things can behave similarly because they have a similar family, and they both are carboxylic acids. So they both have a carbonyl group and they both have an alcohol group. So your textbook has about 20 different functional groups, and you need to be able to recognize them. You do. You don't have to be able to draw them all, but you have to be able to recognize them and know when they're present and that sort of thing. So what we're going to do is we're going to kind of go through them all. And so if you begin, we already know one of them, right? We already know the alkanes. We did that. We said it's a chain of carbons, and those carbons are saturated, which means that we have all carbon-carbon bonds and the rest are hydrogens, right? What we haven't talked yet about are alkenes. Alkenes have carbon-carbon double bonds inside of them. So it could be just one, as is the example right here, or you could have multiple. So this would be an unsaturated hydrocarbon, because remember, to be saturated, you have to use all the hydrogens you possibly could. The next one is an alkane, alkene, and alkyne. So this is kene, alkene, alkyne. Alkyne is a carbon-carbon triple bond. So this removes even more hydrogens. So this is even more unsaturated. So all we're doing is converting from having hydrogen bonds here to having more and more carbon-carbon bonds in the alkenes. Then to the alkane, alkyne, and alkene. All right, so then we move on from our chains. We move on to aromatics. Aromatics are ring structures, and they call them aromatics because they actually, that's why we call them aromatics. And so what we see are a ring structure that's based on benzene. So if you look at benzene, we have 1, 2, 3, 4, 5, 6 carbons, right? And alternating, see if I can erase this. And we have alternating single bonds and double bonds. So here we have a single bond, then we have a double bond, a single bond, a double bond, a single bond, a double bond. And any of the bonds that are not shown are bonds with hydrogen, okay? But an aromatic is always that ring structure with alternating double bonds. Now they could all be carbons. They could all have carbons at each of these corners, or it could be a combination of carbons and then other heteroatoms, like for example, this nitrogen. But they're both still aromatics. Then we have alcohols. Alcohols will always have an OH, right? So if you look at an alcohol, if you look at the carbon that the alcohol is attached to, if it is the only thing that's attached to it is the rest of the molecule and hydrogens, that's a primary alcohol. If we have the carbon attached to an alcohol, and then we have 2 big portions of the molecule, right? Then that's a secondary. So here we only had 1, I can color. Here we only had 1. Secondary, we had 1, 2. Guess what's going to happen in tertiary? Tertiary is just another way to say 3. We have 3 R groups. So regardless, they all have an OH, right, bound to a carbon, OH bound to a carbon. That's what makes it an alcohol. And then however many other groups are surrounding it other than hydrogen, we call it primary, secondary, and tertiary. All right, a phenol. A phenol is a combination of an aromatic and an alcohol. So we already know that an aromatic is our ring structure here, right? And then we already know an alcohol is the OH. So if you have both together, we call that a phenol. And you'll see that a lot in hormones. This one that's pictured here is estradiol. That's the primary female sex hormone. And so you'll see that there are a lot of these functional groups, and they give these molecules particular characteristics. And so you'll see them a lot. Oh, that's another hormone. It has another aromatic and it has another alcohol on it, right? Okay, an ether. An ether is where you have an oxygen, and then I like to say this. So it's an oxygen with stuff on either side. So it's an ether. either side. We have an oxygen with stuff on either side. That's an ether. So here we have an oxygen, and then we have junk attached to either side. So it is an ether. All right, let's see. Let's go on to our next one. Okay, a thiol. A thiol is a sulfur and then a hydrogen. So this first one is a thiol. It's sulfur attached to a hydrogen. You'll see this in the amino acid cysteine. Then you can have a sulfide. A sulfide is very, very similar to an ether, except instead of having oxygen in the middle, you have sulfur in the middle. And then you can actually have a double bond that occurs, not a double bond, you can have a disulfide bond. Di meaning two, so you have two sulfurs. So the di meaning two and sulfide meaning sulfurs. So you have two sulfurs bonded to each other. And then you have functional groups on either side, right? You have those R, whatever all your other stuff is. Let's see, a phosphate. This one's really, really important because we see it in our energy currency of the cell, ATP, right? We all know we need ATP to survive, to live, right? So how do you process that energy, that ATP? We cleave off one of our phosphate groups, right? And we can generate energy that way. And so the functional group on ATP is the phosphate group. So a phosphate group is always phosphorus, and then we have oxygens surrounding it. And some of the oxygens will be charged, and the ones that are not charged will have a double bond. But all you have to do is recognize it. You don't have to be able to draw it. You have to be able to recognize it. Okay, amines. Amines are a nitrogen and hydrogen. So if you've ever smelled ammonia, that's that nitrogen smell, right? You can smell it in urine. That's what makes urine stink. So you have a nitrogen, and that's attached to hydrogens. So that's a primary amine where I have only one R group here. Now, if I start taking away hydrogens and now I have two R groups, that's for my rest of my molecule, right? That tells me I'm secondary. So if I look at my example here, right? What I have are two hydrogens attached to my nitrogen, two hydrogens. And so I only have one attachment. So this is a primary amine. In my next one, I'm going to look, my nitrogen, I have no hydrogens around my nitrogen. So I have 1, 2, 3, 4 different things around my nitrogen. So that's quaternary. Quad for 4, right? So 1, 2, 3, 4 things around that central nitrogen. And that actually makes a nitrogen positive. And if you only have 3 things, that's tertiary, as we talked about before. The other way that your amine, that you can have your amine is if it's protonated. The definition of something that is protonated is an extra hydrogen. And so when you have that extra hydrogen on there, it gives this part of the molecule a positive charge. And so that makes it protonated. And so all of our amino acids have a protonated amine on the end of them. And it's part of the bonding process to bond amino acids together to make a protein. Okay, let's see. See if I can go on to the next slide. All right. Now, the rest of the functional groups that we're going to talk about all contain the carbonyl group, and that's the C double bonded to an oxygen. So carbon double bonded to an oxygen. So we have acetyl group. An acetyl group, and we didn't write in the carbon, but it's really carbon double bonded to an oxygen. But in this case, it's bonded to a CH3, right? So here's our carbonyl group. And what makes this an acetyl group is that we also have attached to that carbon a CH3. So that makes it an acetyl group. And so one example of this is acetyl-CoA, acetyl coenzyme A. You can see it on the very end right here. All right, an aldehyde. An aldehyde just like we said before, it's going to have a carbonyl in it. So here's my carbonyl. And then I'm going to have attached to that carbonyl just a simple hydrogen. Then we have a ketone. A ketone, we have our carbonyl, but then on either side of our carbonyl, we just have kind of the rest of the molecule. So all carbons and hydrogens and that kind of thing. Then we have carboxylic acid. So this is the one I showed you earlier, right? So we have our carbonyl group here, and then what makes it an acid is we have that alcohol group right here. And then the last one is the carboxylate. So it has the carbonyl, but then attached to it is an oxygen, a charged oxygen. And so this is the other side of our amino acid. Remember, we had the amine here, and now we have the carboxylate here. Okay, so my suggestion is to make some flashcards because there are a lot of functional groups. There are a lot of them. All right, so, oh yeah, and we have a few more. I forgot about this. We have a few more that have our carbonyl. Here's our carbonyl, right? In this case, it's bonded to an oxygen, and then it's also bonded to some more stuff, right? So this is a good example of triglycerides. These are fats. Triglycerides, tri meaning 3. So we have 1, 2, 3 triglyceride, right? Okay, so if we look here, we have our double bond, we have our double bond, we have our double bond. Then we're bonded to oxygen, bonded to oxygen, bonded to oxygen. And then here's the R group, R group, R group. It's all carbon. So let's see. Oh, then we have an amide bond. So what we're looking at here is we have our carbonyl group, right? But then attached to it, we have an R group. And then because it's an amide, right, similar to an amine, we're going to have a nitrogen. So we have that nitrogen, a hydrogen, and then some more other stuff from the molecule. And so you could have all hydrogen surrounding the nitrogen. You could have one hydrogen in an R group, or you could have one hydrogen in 2 R groups. Okay. So when you're looking at this, I'm telling you, flashcards, or if somebody wants to make a Quizlet that has like the pictures, you could do like on one side of the slide, you could do the representative structure of the functional group. Like this could be one side of the flashcard, and then the other side, you want the family name. And then you can make another set where you have the family name and an example. And so you would look at the example and go, okay, what's in this structure? And then you could flip the card and it would tell you you have an ester or something like that. So if anybody does want to do it and wants to share with the class, if you send it to me, I'll share with everybody. I don't have any made, but I'm happy to share if somebody wants to do that. Okay, we're going to talk about some more functional groups. This was in the very beginning, right? So if we go back, let's see real quick if we can go back. Here we go. Okay, so remember we had alkane and alkyne. The Y sounds like an I. Ooh, the Y sounds like an I, right? Okay, so we're going to go back and we're going to talk some more about these alkenes and alkynes. So let's see if we can jump ahead again. All right, so alkenes. Alkenes, we said, was a carbon double bound to a carbon. So this is unsaturated. Remember, if we had a single bond and the rest of it were hydrogens, we said that this was saturated. So let's see if I can move this over. This one is saturated. So this is saturated. But if I have a carbon double bound to a carbon, how many oxygens can I put around this carbon? Well, I can only give the carbon 4 bonds, right? So I can only give each carbon 2 hydrogens instead of 3. And so this is unsaturated because you have 1 less hydrogen on each carbon. So when we look at these bonds, a double bond, if you are sharing 4 electrons instead of sharing 2, it's a stronger bond. And so those atoms get closer together, right? So the bond length, so a single bond the two atoms are way out over here. They're only sharing one pair of electrons. If I go to a double bond, the bond length is going to decrease and the atoms are going to get closer together. And this ends up being a much stronger bond. Well, guess what happens? And we'll talk about it in a little bit, right? If you get a triple bond, you're sharing 3 pairs of electrons. And so your atoms get even closer and your bond gets even stronger, right? And so when the alkenes react in some reactions, right, you can break one of those bonds, but usually the carbons remain together, joined by that single bond. And so the alkenes end up becoming more reactive than the alkanes. The alkanes are pretty mellow. They don't do too much, but the alkenes actually participate in more reactions, right? So this is the carbon that I drew for you. This is ethene. Ethene is produced by fruit that's ripening, right? You know, like if you get some new bananas from the grocery store and you had one old banana and you put your old banana in the bowl with the new bananas, your new bananas will ripen faster, right? That's the that's the ethene in there. Alkenes are also found in turpentines. And those are in like beta carotene. I'm trying to think of other ones that y'all might have heard on, but beta carotene is probably the one you've heard of the most. But from a turpentine, you can actually make some really, really important molecules for the body, like cholesterol and testosterone and estrogen. So when they undergo reactions, they make lots of really important molecules for our bodies. So now we're going to, guess what? We're going to lose some more hydrogens and we're going to make some carbon-carbon triple bonds. So what I have down at the bottom, right, is my same 2 carbons, but now I have a triple bond between the 2 of them. And now I can only have 1 hydrogen attached to each carbon. And so these alkynes are even more reactive than the alkenes. And so because they're so reactive, we typically don't find them in nature because they end up undergoing a reaction and they're no longer an alkyne. So you probably know one, you probably know acetylene. Acetylene is the fuel that welders use inside of their welding torches. And so it's very, very reactive, very dangerous. Okay, then we can take our hydrocarbons and we can put them into a ring. And we've talked about this, right? When we talked about the cycloalkanes. And so anything that turns into a ring, we call this an aromatic. And we call them aromatics because they actually really smell good. It's kind of cool. So the aromatic compounds have that cyclic circle structure, right? And we call them, when they're part of a bigger molecule, we call them a phenol, right? And that was in our groups. But all the carbon-carbon bonds of benzene are the same length. And I'm going to talk about why that is. It's a very stable configuration, and it helps to make these molecules very stable and to resist reactions that would break the bonds. So why is that? Well, if you look at the molecule, right? Let's zoom in just on these. So this is the molecule we start with. If we look at some specific carbons, right? If we call this carbon 1, carbon 2, carbon 3, carbon 4, carbon 5, carbon 6. Initially, we have that double bond between carbon 1 and carbon 2. But what can happen is that the electrons can move around and actually move their position. So this double bond could move over here, which would make this area now a single bond. And that's what we see in this new picture. We have our double bond in a new place, and now here we have a single bond. But that creates kind of a chain reaction, right? And this double bond will move down here, and this double bond will move here. And that's exactly what we see. So these 2 molecules that are drawn all over are actually the same thing. And we call this resonance. resonance. So those double bonds can move around. And so what we see is that when we take like a snapshot of these molecules, we don't actually see a single bond, we don't actually see a double bond. What we actually see is something that's an intermediate. So if this is a single bond, you know, this far away, and this is a double bond, what we see are the molecules are basically right in between a double bond and a single bond length. And so they're all like that. All the bonds are the same length, and it's very, very stable structure, right? And so all the electrons in the double bond are shared evenly among all those carbons. And so sometimes what you'll see is instead of seeing those double bonds, we want to represent that they can move around. And so we actually represent it as this last structure with just a circle on the inside, meaning that those electrons are just free to move around. They can be shared all over those carbons. And so it makes it very stable. And so these molecules are much less likely to react with basically anything else. They're very, very stable. Then we have some other unsaturated hydrocarbons. So our aromatic functional group have 2 or more benzene rings, right? And so if you have 2 or more benzene rings, we call them polycyclic. What does poly mean? Poly means many, and cyclic just means that we have that ring structure. So they're polycyclic aromatic compounds, or PAHs. But I like saying polycyclic because it reminds me poly meaning many and cyclic meaning ring structure. So we have multiple. You'll find them in tobacco smoke, right? And a lot of them have been shown to be cancer causing, or we call that carcinogenic. But it's also useful. They're also in components of a lot of different plastics that we use on a very, very, very daily basis. So can be good, can be bad. Maybe just don't put it in your body. All right. There are some functional groups that are very important in how we treat patients. And so anytime you have a drug that you're prescribing, that you are being prescribed, or you are prescribing, however it ends up being, you get this little folded up sheet of paper, right? And you unfold it and it's this teeny, 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 tiny print. So one of the things that you have on there is a chemical structure. So you actually see the molecule on that little handout of information about the drug that you're taking. And what we found is that we can make molecules that look similar. And if they look similar, if they have the same similar structure, what we can see is that they're going to perform pretty similar functions. So we're looking at some examples of that. And the top 2 are opioids. They are pain relievers, and they're very, very strong, right? Here we have morphine, and here we have oxycodone. These are 2 very, very heavy duty narcotic pain relievers, right? You cannot get them without a prescription. And so some people actually become addicted to morphine or oxycodone. And one thing that patients are sometimes prescribed is what's called Narcan. So this is the chemical name, but lots of people call it Narcan. I don't know if y'all have heard of this, but you can give someone Narcan. So if you look at the structure of Narcan and our 2 opioids, our morphine and oxycodone, are very similar. They're not exactly the same, but they're very similar. And so what happens with Narcan is that you get the same pain relief, but you don't get the change in cognitive abilities, and the part of the molecule that makes it basically addictive is not in Narcan. And so because the structures are similar enough, it's a way to wean patients off of the morphine or the oxycodone. And so you'll see that to treat people who are abusing prescription medications. All right, let's see. Now, lipids. Lipids are a really interesting kind of category of molecules. They're hydrocarbons. So remember what a hydrocarbon kind of looks like. Let's see. For me, the picture's covering it. Let's see if I can do this. Okay. So here's a fatty acid, right? There are two things that are going to be inside of fatty acid. Hydrocarbon. And remember we said hydrocarbon is just carbon, 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 and then cover it in hydrogens. But they also have a carboxylic acid group. So remember we have a carbon double bond to an oxygen, and then we also have our alcohol group. So our carbonyl and our alcohol group. So carboxylic acid is two functional groups kind of basically put together. And so when we talk about fatty acids, right, I know you've heard, oh, it's monounsaturated, it's polyunsaturated, which one's good, which one's bad? Well, if you have no double bonds, right, that's a saturated fatty acid. So it's got lots of hydrogens. If you convert one of those single bonds to a double bond, that is a monounsaturated fatty acid. So it's a fatty acid that has this chain, and one of those single bonds is a double bond. Now, if you have two or more double bonds, now we're called polyunsaturated fats. So it's still unsaturated. We don't have all the hydrogens, but we have multiple places where we have double bonds, right? And so that's the difference between monounsaturated and polyunsaturated. So when we talk about our saturated fatty acids, this is an example of a saturated fatty acid. I have no double bonds here. So these are long, these are straight chains. They're alkane-like, so it looks like an alkane. They don't have any double bonds, but this R group is actually a carboxylic acid group. So if you took this, excuse me, if you took what's here in red, right, these R's, and you just replaced them, you would have a fatty acid. So if I took this and I moved it, right, so, and I removed the R's, and then I push this on here, right, now I have my fatty acid. So that would be an example, this would be an example of a saturated fatty acid. So it's no double bonds, but we still have our carboxylic acid group at one end. So we need these fatty acids. You don't need too many fats in your diet, but you do need some fatty acids. And so all the fatty acids that are really important for our bodies usually contain 12 to 22 carbons in this chain. And if you look at all the naturally occurring ones, it's kind of interesting. You find that they're all even numbers of carbon atoms in those chains. So if we look, for example, at some of them, what you'll see here is your alkane, right? These are all saturated. These are all single bonds. And then we have our carboxylic acid. So we have our alcohol group here and our carbonyl group right here. And so if you look at the natural sources, right, in coconut, we have something that's 12. So look at all these, see how they're even numbers? They're all even. In nutmeg, you have mystic acid. You have palmolic acid in excuse me, in palm. In animal fat, this is if you'd had like bacon grease and that kind of thing, you'd have 18 carbons in the chain. Peanut, there's fat in peanut, in any kind of nut, right? You're going to see about 20. Canola oil, this is pretty much what a lot of people cook with, right? That has 22. So we need fats in our diet, right? They're really, really important in covering the neurotransmitters and in covering the neurons that allow neurotransmitters to send signals in our brains, right? They're really important for covering our internal organs and protecting them from damage. And so we need to have some, but everything in moderation, right? So the FDA recommends a maximum of 30% of the calories that you normally get in your diet come from fatty acid. And they recommend that most of the fat that you take in is either monounsaturated or polyunsaturated fatty acids. And so if you look at the different sources of fatty acids, right? What they were suggesting that we eat is to get the most that you can from the mono and the polyunsaturated. So if you look at the mono and the polyunsaturated, those are the ones where you want to have more of. So you want to have less of the blue, more of the red and the green. And so like, you know, olive oil, people say use olive oil. That's a good one. There has been kind of a push, and your book actually talks about it, about coconut oil. And you can see there's a lot of saturated fat in coconut oil. And it hasn't been proven that it's that much, that it's really healthy for you compared to the other oils. They really do still think that having more of the monounsaturated and polyunsaturated is better for you. So you got to kind of watch the literature on that. Okay, so now we're going to go on to our in-class problems. So let me pull that up. All right, and I put myself this note to remind you to make flashcards, but I did mention it earlier. So when you're making your flashcards, you want a name versus a picture of like an example. Whoa. So picture example of your family. And the other one I didn't say, but would be a good one, is the name and then the description. So sometimes in an exam question, I might give you a picture and sometimes I might give you a description. So you should be able to do either one. And then you also want to be able to recognize the functional units within an example molecule. And so I'm thinking Quizlet might be a really good place for that. Okay, oh no, I have all my answers on this one. Hang on. Okay, now I fixed it. Now we can do it together. Okay, so identify the family of hydrocarbon present in the following. So this is what you'll have to be able to do. You have to be able to look at this and say, what do I see? And here I can see that I have a carbon and it's triple bonded to another carbon. So that's kind of strange. Let's see if I can change that. All right, so when I see that I have that carbon triple bonded to a carbon, I'm gonna have to think, okay, so that's my al something, because all I have is carbons and hydrogens, Al, and this is gonna be on my alkyne, Y-N-E, alkyne. And so that's carbon triple bond to a carbon. So that's what you have to realize for that one. The next one, if I'm looking at this, what do I see? I can see that I have a chain of carbons, but in that chain of carbons, I have 1, 2, 3 double bonds here. So for this one, I need to remember my name for my double bond, and that's an alkene. Okay. The next one, I have a cyclic ring, but I only have 1 double bond present here. So this is going to be a cyclo, cyclo alkene, right? Alkene tells me carbon-carbon double bond, and cyclo tells me it is a ring. Okay, so let's go on. Now, identify the family of hydrocarbon present in the family. So we have, I see here, now be careful with this. You should look at this and you should know that that's actually a carbon double bonded to a carbon, and this carbon has 2 hydrogens, this one has 1 hydrogen, and then it's attached to another carbon. So be careful that you realize that it is not a hydrogen double bound to a carbon, that you recognize that that is there's a double bond between the 2 carbons. And so if I see that, then I'm going to automatically know, what do I have? Oh, why am I doing this? This is the one we're supposed to do in class. Okay, but that's okay. I'll finish this one. So we have an alkene because this is a carbon double bonded to a carbon, right? I'm going to leave the rest for class. My goodness. Doing too much here. All right. Okay, identify all the functional groups present in the following. So whenever you hear that, identify all the functional groups, that's usually a pretty good indicator that there's going to be more than one. So what you should be looking for are some common things that are inside of it. And so what I automatically see is I have a carbonyl here, but that's not all. I have that carbonyl, but there's some other things going on. And so sometimes it helps me to write out what I see. To write out what I see and not in just stick figure, right? And so I know I have a carbon that's double bonded to an oxygen, and then I have an oxygen, and then that oxygen is bound to some more stuff. So that is a functional group that you know that is an ester. That's an ester, okay? Because we have oxygen and we have stuff bonded on either side, right? What else do you have here? You also have a nice, beautiful ring here that has some double bonds. So this one right here, that is going to be an aromatic. And I know it's an aromatic. It's not something cyclic. It's an aromatic because I have those alternating double bonds on a benzene ring, on a 6-carbon benzene ring. All right, and I see one more group right here. This is a nitrogen, and it's bound to 2 hydrogens, so it only has one R group attached to it, right? So if I were to draw this out, I would draw my nitrogen. I would draw my nitrogen, and then I would have 2 hydrogens attached and an R group. So my functional group is right here. It's the same thing as what I highlighted on the actual structure. Either way, however you're looking at it, this blue part here is a primary, because it only has one R group attached to it, a primary amine, right? And that means it has that nitrogen in it. All right, let's see. What's our next structure? We have to indicate them all. So our next structure, okay, I see that I have a carbon chain, and in that carbon chain, I have a double bond. So that's really carbon double bonded to a carbon. So that's an alkene, right? That's an alkene. Okay, but then what I also notice over here is that I have a sulfur group. So this is a sulfur bound to a hydrogen. So let's see if I can draw that. So a sulfur bound to a hydrogen, and then I have an R group attached to it. So whenever I have that, what I know is that this group right here is a thiol. Thiol, a thiol. Okay. So I'm skipping the even, we're going to the odd. All right, the most prevalent fatty acid in coconut oil is lauric acid, a saturated fatty acid containing 12 carbons. Draw lauric acid in skeletal structure. So whenever you see the words fatty acid, you should be thinking about 2 things. You should know that you have an alkane, ALK, an alkane, and we know it's an alkane because it is saturated. This means no carbon-carbon double and no carbon-carbon triple bonds. So we have an alkane chain, and because it's a fatty acid, that acid you should be thinking carboxylic acid. Right? So I'm going to draw, let me draw my chain first. I need 12 carbons. So remember, we're starting out, that's 1 carbon. So that's 1, 2, here's my second carbon, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And there I'm ending on my last carbon there. So that last carbon is double bonded to an oxygen, and then that carbon is also bound to an OH, because that's our carboxylic acid part. So the carboxylic acid part is right here, right? Because we have that carbonyl group, and then we have the alcohol. And then our alkane chain right here is all the rest of this molecule, right? I know my artistic abilities. They're terrible. All right. And that's it for that section. Okay.